Hi. First of all, thanks a lot for invitation. It's really motivating to see how many people care about quantum computation. I didn't know about it. And it's also nice to be in Florida. All right. So as Andrew said, I'm a physics professor at the University of Minnesota. How do I operate it? Oops, yes. And I want to tell you a little bit about science of quantum algorithms. I'm a condensed matter physicist by training, and I spent a lot of time thinking about physical qubits, superconductor, semiconductor interfaces, whatnot. But lately I was thinking more about algorithmic side of the problem. And two excellent graduate students were extremely helpful to teach me about it. Han-Teng is now a postdoc in Shanghai, and Shu-Chun is at NYU. All right, so I probably can skip a motivation in this audience. So we have quite a few prototypical quantum computers accessible to all of us. And what it would be nice to have is an actual demonstration that there is a quantum supremacy, not the sort of theoretical quantum supremacy, but something real-life problem which can be more efficiently solved in quantum computer. And I thought that the I wonder, oops, yeah, now I understand how it works. Yes, so I thought that optimization, and in particular quantum optimization, can be a good starting point. It's clearly a useful problem. Now, can we solve it quantum mechanically more efficiently than we do it classically? So for starters, what you want to have a computer scientist what called bit strings, namely the sequence of zeros and ones. Whatever your problem is, the answer is always a computer bit string, right? And you want to find the best bit string, namely the best sequence of zeros and ones, and physicists prefer +1 and -1 because that allows us to think about spins, binary magnet, up or down, plus or -1. And this particular bit strings or spin configuration in a physicist language, they should optimize the cost function. So you give me a cost function, I give you a solution, you calculate it in no time, you tell me is it a good solution or is it a bad solution. So for example, the simplest one which physicists like, but not necessarily the most useful practically, is just to take a matrix and calculate a matrix product of your bit strings with some matrix Jij. By the way, if you take this matrix just at random, each element taken completely at random, this is an extremely famous physics problem known as Sherrington-Kirkpatrick model. And as recently as 2021, Nobel Prize in Physics went exactly for understanding what this model does. Admittedly, the work actually was done in late 70s. But I'll tell you a little bit more about some more recent development in the field. So how the classical optimization works? So you have 2 to the power n, exponentially many, and that's the problem, possible bit strings. And you want to find the one which is the best, ideally. Now, I'll tell you a little bit more what I think by this many-body localized or delocalized states that will a little bit premature on this slide. So if this problem is NP complete, so and you really need to try 2 to the power n different solutions, physicists will call it spin glass, and Andrew already used this language before. So first of all, what's the classical annealing? Classical annealing is a very simple protocol where you at random pick a spin, pick a position in this string, and flip it. And then you check your cost function. Is it better than before or is it worse? If it is better, you accept it with some probability. If it's worse, you reject it again with some probability, and then you keep doing. And you hope that in this way you will be able to step by step improve your cost and find the best one. Now the problem with this is that in a space of all possible spin configurations, and I'm plotting one-dimensional space for just not being able to plot anything better, the actual space has exponentially many dimensions. But the idea is here. In this space, you have many minima, local minima, which are not necessarily the best. Most of them are not good. But your classical annealing algorithm will be stuck in one of these minima. And then you will not be able to proceed. Because you flip one spin, it's bad. You flip another spin, it's still bad. So you think you find a solution, but actually you didn't. Actually, you're stuck in one of these false minimas. So now here the quantum comes about. Why quantum? Because we were told that quantum mechanics allows for tunneling. So what is tunneling? Tunneling is an ability of something to penetrate the wall, namely penetrate a potential barrier. Namely, if you're stuck in one of these minimum, if you allow for quantum mechanics, namely for tunneling, then maybe you will be able to escape and find a better minimum. So now there are two problems here. First of all, can you really escape, and how much quantum you have to be to go away? So that's what is called localization or delocalization. So we are particularly interested in delocalization. We want to explore many minima in this potential landscape. And what people understood in the last 20, maybe 15 years, that this process happens abruptly, as a phase transition. So you increase degrees of quantumness, whatever it is. I'll give you an example in a sec. And all of a sudden, you, boom, go from state being sitting in one minima like this to being spread over many minimas here. So the fact that this is a phase transition and not a crossover is an extremely important observation, because that allows you to immediately understand quantitative properties of this process, how things scale and how things behave. So that I will explore a little bit later. So to make a problem actually quantum, what you want to do, you want to add something to your cost function. So in a physicist language, you want to make your cost function a matrix which is not commutative. Different parts of this matrix cannot commute with each other. But that doesn't matter probably for you. The only thing which does matter is that it is very easy to do technically. You can add these non-commuting parts, and that's as easy as program everything else. So that's, by the way, the set of energies or costs of these states, different solutions, as function of the degree of quantumness. And somewhere along the way, you can see that there is a transition. I wouldn't go into detail to try to explain the details. But let's proceed. So the question is, now we have this tool to make things quantum as opposed to classical, but is it really helping us? So the first news is that there are no free lunches. It's not news. You still cannot find an absolute minimum of your function, of your cost function in a polynomial time. You still have to spend exponentially long time to do it. That's OK. Why? Because we probably don't need the absolute best. We can settle with the second best. Namely, we can allow yourself certain tolerance to deviation from the best solution, which I call delta, and you can find a bit string, a solution, which will have a cost function in a range of delta from the absolute best. If we can do that, and if delta is sufficiently small, probably we're good enough. Now, what you can do is now you're in a better shape if you're allowed to be approximate. Namely, you can solve this problem in a polynomial time, polynomial both in a system size, number of constraints involved in the problem, and polynomial in this tolerance. And there are certain algebraic exponents called alpha and beta in this slide, which tells you how fast actually you can perform as function of system size and as function of your tolerance to mistake. Now, classical computation can do the same. It also has the same scaling. So the question is actually whether quantum exponents alpha and beta are better, more advantageous than the classical ones. And what Andrew showed us in his talk, actually, that it is. It's not a predetermined answer in any sense. And maybe it's not even valid answer for all the problems. But at least for some problems, what they demonstrated, which is very exciting, is that quantum exponents are indeed better than classical. So you can do things in a shorter time and with better tolerance. All right. Right. So another thing to pay attention is that these exponents are actually legacy of this phase transition, which I mentioned before. So every phase transition in physics, or most of the phase transition in physics, come with certain critical indices. And it is precisely these critical indices which tells you how fast or how slow your quantum computation is going to be. Now, so that's the graph which I steal from Andrew and company. So it's supposed to demonstrate here two things. One is that the exponent is indeed better, namely the slope of the blue line here is steeper than two other lines. But the second point is that the quantum computation doesn't follow this blue straight line for a long time because there is a decoherence problem. So there are, there is a price to pay for everything in life. So here we have to pay a price that your computation cannot be too long. So what I'm going to tell you about that it possibly is not such a big trouble. And that can be overcome by the following idea. You can do your calculation in cycles, each cycle being relatively fast, which doesn't require extremely long coherent times, but doing, first of all, many cycles in a smart way. I'll explain in a sec. And second, taking an active feedback decision in the end of every cycle can allow you to do things to harness both of, goods of the two worlds. You use quantum exponents on the one hand, and on the other hand, you don't need extremely long times. That's coherent times. That seemed to be a good idea. All right, so how do you achieve it? So the idea is that since you want to find the smallest energy, that's essentially mean that you're cooling your system. So all what quantum and classical optimization do is actually sophisticated way of saying that we cool the system. Okay? Now, as we all know, cooling is a relatively easy process. You take your kitchen fridge, and it does cooling for you. Okay? Now, how does it do? It works in cycle. It takes a working body, which is free on gas, and you compress it, you pass it through your fridge, then you do heat exchange on the back of your fridge, and then you decompress it. And then you dial repeat. You do it again and again and again and again. So pretty much the same idea here. In quantum computation should also be working as a kitchen fridge, namely you cyclically cool your working substance, which is an array of qubits now. Not a free on gas, but array of qubits, but so what? So here is an idea, an example rather. You can arrange it in the following way. First of all, in a classical problem, you can always arrange that you can find, in some way you can find a local minima of your optimization problem. Suppose you do it with a classical computer, or you find it in a previous cycle of your quantum computer, you found it. So now you have a certain bit string, and you call it a reference string, whatever it is. And now it's very easy to arrange for an auxiliary problem where this reference string will be exact minimum, exact ground state of your system. You simply add a magnetic field in a z direction, which is at every qubit coherent with collinear with plus or minus configuration of your chosen bit string. Now, of course, in reality, they don't apply magnetic fields. They have a much smarter way to manipulate it, but that's what they know to do. So you can very easily, very fastly, arrange for your chosen bit string, chosen state, to be a ground state of new problem. That's good, but that's not the problem which you wanted to solve. That's another problem. So you need to go back to your problem. And here is the thing that, okay, I probably can skip this, that you can go in cycle. And in my simple example, the cycle is in 2 dimensions. So do I have it in this slide? No, okay. Let me go back. So the cycle will be in 2 dimensions. So one of these dimensions is this auxiliary field, which allows me to bring my chosen state to be the ground state. That's called Bz here. And the vertical axis here, which is called Bx, this is degree of quantumness of my problem. So now the thing to notice here is that in this 2-dimensional space, where I'm going to arrange my cooling cycle, it's a phase diagram. And there is a couple of phase transitions in this phase diagram. So the full red line is this fancy transition between spin glass and a paramagnet. Why is it fancy? Because what we now understand is that at this transition, your quantum state goes from being localized in some local minimum to, boom, exploring all many minima. So which is good. So just go there, and you will be fine. That's not quite simple, because when you explore all of these minima, you explore also minima which has higher energy and lower energy. So the question is, how do you navigate your system, the state of your system, to specifically to lower minima, and you avoid those which has higher energy. And apparently that's possible if you do this cycling. So another important thing here is that there is so-called tricritical point, which connect first-order and second-order transitions in this working substance. So pretty much like your Freon gas undergo liquid-gas transition, so the working substance, the spin glass of your quantum computer undergoes transition between a paramagnet and the spin glass. So if you want to have a good refrigerator, you want to go around this phase transition. So that's how you do it. So you find some approximately good minima. You go in step 1 to auxiliary problem where this minima is an absolute minima. It's an easy step, and you arrive to the situation where your state is a ground state, and it's separated from all other states by a big gap, and you can make this gap as big as you wish. So then you increase degree of quantumness. That's, again, not a big deal, because now your state of your quantum computer is separated from all other states. There are no danger of leaking to other states. But then finally, you have to go back to your problem. And that's, of course, where the troubles start. So the observation is that if you do it sufficiently close to this tricritical point, and I have to be careful what means sufficiently close, but if you do it, then what happens is that you can leak only to states with smaller energies and avoid those states which have higher energies. Okay? So you come back, you do in the end of the cycle at point 4 in this phase diagram, you do your measurement, and you determine new state. And if you like this state, you take it as your new reference state. If you don't, you adjust your cycle, adjust this, let's say, slopes of these lines, and you repeat the cycle. And then if you do it properly, you're guaranteed step by step decreasing temperature, namely finding better and better solution. And again, thanks for what we heard from Andrea, the critical exponents, the scaling of this process is better than what you can expect in a classical board. All right. Yep, I'm probably close to the end of my talk. So I'll skip the technical details. Yes, I'll skip this. This is a simulation on a classical computer, how this process looks like. So that's to say that we do understand approximately how it works. So so that thing demonstrates that if you do it sufficiently close to the tricritical point, then the number of states with higher energy is less than the number of states with a lower energy. And both of these things scale with some algebraic exponents as a function of tolerance and as a function of deviation from this tricritical point. And we know these exponents to some extent due to our simulations. And they tell us that, indeed, it seemed to be better than what you'd achieve in any classical annealing we know today. All right, so I'll probably try to wrap it up and give you a summary. Oops, that's unexpected. So again, the takeaway points from my talk are the following. You should think about, or you may think about, quantum computation as a refrigeration. And refrigeration goes in cycles, and these cycles have to take you through some phase transitions, maybe liquid gas as is in our fridges, or in this case, it's a transition between many-body localized spin glass and delocalized paramagnet. That's what comes instead of liquid gas. What else? Right, so you have to be careful to melt it through first-order transition and refreeze it through the second-order transition. That's details of arranging the cycle. Yes, the very important part of the story is after each cycle, we need to decide. It's a fast and easy process, but we need to inject our intelligence after each cycle, whether we want to accept or reject a new state we obtain, and how to adjust the cycle, parameters of the cycle for the next cycle to take advantage of what we know before. All right. Yep. And again, with critical exponents, which allow time economy of time for quantum computation, are apparently better than what we can do in a classical annealing story. And again, thank you for inviting me here. It was a pleasure to be. Thank you.
Excellent presentation, Alex. And we just have one question online. What is the time scale of each cycle in this iterative process you were describing?
Very good. Very good question indeed. So for full disclosure, the lower in energy you go, the farther you cool, the slower the cycle has to be. Yet, it doesn't have to be extremely slow. So, if your coherence times of your machine allow you for longer cycle, you probably will be able to have success rate of getting new state with lower energy in 1 cycle, in 2 cycle, in 3 cycle. If you do it faster, then maybe every 10th cycle will give you a better state. Okay? But it will. It's guaranteed. You don't have to do exponentially many cycles. That's the point. You do only power law algebraically many cycles, and you guarantee to find a better state. And how many cycles you have to try depends how long your coherence time allow you to do each cycle.
Thanks, Alex. Thanks. That's terrific. Well, that's our last question for you, and I have a question for Andrew, so I'm going to call him up on stage. Let's thank Alex Kamenev again for his great presentation. Thank you.